Welcome back. Did you think about why this did so much better in terms of percent error than burning a chip openly in the fume hood? Well, it has everything to do with isolating that heat, doesn't it? The cut does a great job of keeping the heat in, keeping it contained with the water, with the metal, where the metal can transfer its heat to the water. But when you have the chip burning openly in the fume hood, that heat is being lost to the surroundings, and it's not able to heat the water inside the beaker. So, when we see this calorimeter, we understand that it does a whole lot better job of being efficient in allowing that heat transfer. Last time we talked a lot about thermochemistry, some of the definitions and so forth, and we're going to talk more about chemistry today. Stick around. Now, you might recall seeing these two equations, the ones here at the top of the board. This one actually produces quite a bit of heat energy. It is exothermic. It produces heat. Remember that. This second one requires energy. Energy would actually be a reactant in this equation. Because of that, we think of it as absorbing heat. It is endothermic. And as a matter of fact, this reaction feels cold when you touch it. This reaction feels very warm. This one is used quite often in hot packs, this one in cold packs. Now, I'm going to show you a third type of what we call thermochemical equation. That's what these are, thermochemical equations. They show not only the state of matter involved with each of the components, but also the heat involved as well, the enthalpy involved with this reaction. So this third one right here is one that goes on in your body all the time, every day. This is glucose, blood sugar. And so when your body burns glucose, it uses oxygen to do that. Breathe it in, and it helps to burn that glucose. It produces carbon dioxide gas and water. Now, look at this. It also produces a lot of heat energy. 2,808 kilojoules for every mole of glucose that's burned. Notice that there's a negative there. Yes, this is an exothermic reaction. Is it any wonder that we are warm-blooded? Now, notice also I've put right here COMB. That refers to combustion. The heat of combustion, or the enthalpy of combustion, is the enthalpy change when 1 mole of a substance is completely burned. Also, we notice this little zero mark right here. What this means is that when they perform these experiments to decide what the enthalpy is, that they do so at what we call standard conditions. This is a little different than standard pressure and temperature. Standard conditions, 1 atmosphere, so that's the same, but the thing that's different is they do it at approximately room temperature, 25 degrees Celsius. They want to get kind of a real world view of what's going on. So these again are thermochemical equations. They tell us states of matter. They tell us, of course, the reaction, but they also tell us the heat energy involved in that reaction. I thought you might also want to see some heats of combustion or enthalpies of combustion for some other everyday substances. For one, table sugar. Wow, table sugar has quite a bit of heat energy that it releases. 5,644 kilojoules for every mole of table sugar. Octane, a component in gasoline. Octane releases 5,471 kilojoules for every mole of octane. Propane, you might make your hamburgers with propane, I don't know. The heat of combustion there, negative 2,219 kilojoules per mole. Each of these, of course, are exothermic. Interesting to note that propane doesn't give off as much heat as 1 mole of glucose does. Fascinating. So again, thermochemical equations, heats of combustion, exothermic, endothermic. Now, chemical reactions aren't the only thing to produce or to absorb heat. Phase changes can do that as well. For example, if I take ice and I'm trying to melt the ice, I notice that when I get to the 0 mark, the ice doesn't immediately convert to liquid. It takes a little bit of doing, doesn't it? Even though the temperature's not increasing on that ice while I'm converting it to water, it still takes some energy. And also, whenever water goes from the liquid state to the gaseous state, I notice that when it comes time to boil, even though my water may be at 100 degrees, it may take a little bit of time for all of that water to convert to steam. It doesn't all convert at the same time, does it? We call these heats of fusion and heats of vaporization. And what they are is that these are the energy amounts that are required to overcome the intermolecular forces. Now, up until that point, up until the point of, say, melting, I've just been adding heat energy, increasing the kinetic energy of that substance. But once I get to the phase change, the point at which it melts, the water melts, for example, that's going to require energy to overcome the intermolecular forces between those molecules and allow them to flow more freely until everything there has been converted to water. Likewise, with the gaseous state, with the change to gaseous state, I require energy to overcome all those intermolecular forces between the molecules to convert from the liquid state to the gaseous state. Again, heat of fusion and heat of vaporization. Here is the conversion of solid water to liquid water. And notice that the heat of fusion, in other words, the energy required to convert 1 mole of that water from solid to liquid is 6.01 kilojoules for every mole. In other words, 18 grams of water in ice form, I'm going to require 6.01 kilojoules to convert all of that ice, the 18 grams of ice, into 18 grams of liquid water. When I convert from liquid to gas, there's a heat of vaporization. Overcoming those intermolecular forces, converting from liquid to gas, it requires 40.7 kilojoules per mole. That same 18 grams of liquid water converted is going to require 40.7 kilojoules to convert all of that into gas. Let me illustrate this graphically for you. So I'm going to illustrate what happens temperature-wise with 1 mole of water, or 1 mole of H2O. Here it's in the ice stage, the solid stage, and let's say it's at 50 below right now. I'm going to add energy. I'm going to add kinetic energy to these molecules. What's that going to do? It's going to cause my temperature to increase, isn't it? Until I get to the point at 0 degrees Celsius. At this point, I have to convert from ice to water. That's going to require 6.01 kilojoules for me to do that. In other words, I'm going to have to add 6.01 kilojoules just to convert everything from ice to water. And then and only then that water can begin to increase in temperature again. Do you see that? The temperature is going to remain fixed while I'm undergoing fusion, while I'm undergoing the conversion from ice to water. And then again, I have the water that's increasing in temperature until it gets to 100 degrees Celsius, in which case then I have to convert from water to steam. The amount of energy required to convert from water to steam, 40.7 kilojoules. Now, by the way, these are not to scale. They're just to prove a point. So from water to steam, notice again, my temperature, that's supposed to be level, by the way, sorry. Water to steam, that temperature does not change. While all those molecules are being converted into steam, you may have a few convert, and then another few convert, another few convert. So it takes 40.7 kilojoules for that 18 grams to completely convert into steam. And then after that, the temperature will begin to increase again as the kinetic energy causes those steam molecules to move even faster. Does that make sense? So we have heat of fusion here, heat of vaporization here. But listen, those numbers also go for the conversion of steam to water. In this case, they would lose 40.7 kilojoules of energy converting from steam to water. So let's say I had 18 grams of steam and I allow it to cool, and it's losing energy to the surroundings. As it gets to this point right here, now it has to lose enough energy to allow those intermolecular forces to re-engage and to pull this into liquid water. How much? 40.7. So when we lose the energy, we of course would add a negative sign. That water will continue to lose energy as long as I allow it to cool until it gets down to the 0 mark. And again, converting from water to solid ice requires that I lose enough energy so that those intermolecular forces can take hold and give me solid ice. How much? It has to lose 6.01 kilojoules. Heats of fusion and heats of vaporization can go both ways. So just to recap a little bit, my heat of fusion going from solid to liquid requires that I absorb 6.01 kilojoules for every mole of water that I'm heating. Going from liquid to steam, my heat of vaporization is 40.7 kilojoules for every mole of H2O that I'm converting into steam. The other way, going from liquid to solid, freezing, my change in heat, my delta H will be negative 6.01 kilojoules per mole. Notice, it's the same amount. It's the heat of fusion, just negative. It's giving away that energy. Going from gaseous water or steam to liquid requires that I release 40.7 kilojoules for every mole of H2O that I'm converting. You get it? It's just directional. Incidentally, it's this principle of heat of fusion that allows farmers to protect their crops when it gets cold. Let's say we're talking about an orange farmer. Now they usually grow those in the lower, more southern states where the temperatures don't get close to freezing very often. But when they do, that farmer will do something that might be curious to us at first. He'll spray his crops with water, especially if it's going to get down, if the temperature is going to get down around the low 30s or even the high 20s. The farmer will spray his crops with that water, and in doing so, that water, when it freezes, will release heat energy. So for the water that's clinging to those oranges, that water, as it freezes, will release heat energy. Where? To its surroundings. What are the surroundings? The fruit. And that's why farmers will do that to protect their crops. You might have a problem that's this easy, where you have 3 moles of H2O converting it from ice to water. The heat of fusion, which would be given to you in this case, is 6.01 kilojoules per mole. All you have to do is multiply for each mole you have. 3 moles multiplied by 6.01 kilojoules per mole. The kilojoules are left, the moles cancel, and you have 18.03 kilojoules. But let's take it one step further. Now here's one that's going to require us to break things up into sections. 63 grams of H2O converted from ice at 50 below Celsius to water at 50 above Celsius. Calculate the total heat. And heat, of course, is Q. Just to make the difference here, enthalpy is usually given to us in joules per mole or kilojoules per mole of heat energy that's involved. Here we're talking about the total heat in this system. So let's break it down using what would also be given to us. The heat of fusion of water is 6.01 kilojoules per mole. The specific heat of ice is 2.11 joules per gram degree Celsius. And the specific heat of water, as we've used so far, is 4.184 joules per gram degree Celsius. So let's break it down. By the way, let's talk for a second about why we have to break it down. We see here the gradual increase as we're heating the ice, as we're adding energy to the ice. The temperature keeps rising to a point, and then we have melting. But notice that during the melting process, there is not a change in temperature. So because of that, our normal Q equals M times C times the change in temperature, that's not going to work for us. It will for this point right here, and it will for this point right here, but not this point. That's where we need to use the heat of fusion. So we're going to break this into 3 stages. Let's find the heat for phase 1. The time in which that temperature is going to be steadily increasing from -50 to 0. We have Q equals M times C times the change in temperature, Q equals MCAT. The mass is 63 grams. The specific heat of ice is 2.11 joules per gram degree Celsius. Remember, we're still in the ice stage, aren't we? And then, what's the change in temperature? 50 degrees. Going from -50 to 0. That gives us a total of 6,647 joules, or 6.647 kilojoules. We divide the joules by 1,000. Let's do phase 2 now. For phase 2, we're calculating the heat from ice to water. Still, same temperature all the way, so we can't use this equation. We use this one, the number of moles times the heat of fusion. To do this, we convert the grams to moles. We do this by dividing 63 by the molar mass of water, 18, and that we multiply by the heat of fusion, 6.01 kilojoules per mole. We get an answer of 21.04 kilojoules. This is the reason why I converted this to kilojoules. We're going to need for all of our units to be the same. We've got one more phase to go. For the final phase, 0 to 50, we go back to using MCAT. Mass times specific heat of liquid water times the change in temperature. 63 grams, law of conservation of mass, right? We haven't lost any mass here. 63 grams multiplied by 4.184 joules per gram degree Celsius, the specific heat of water, and the change in temperature, 50 degrees. That gives us 13,180 joules, or if we divide by 1,000, 13.18 kilojoules. So, all that's left is to add these 3 phases together, and that will give us the total heat. From stage 1, stage 2, and stage 3 gives us 40.87 kilojoules, but we round to 3 significant figures because our original was given in 3 significant figures. So we get 40.9 kilojoules. What? 2? You think there were originally 2 significant figures here? I think you're crazy. Here's one for you to do. And let's see if you can get the answer and just email me your result. If you have 360 grams of glucose and the enthalpy of combustion of glucose is negative 2,808 kilojoules for each mole, calculate the total enthalpy involved with 360 grams of glucose. Give it a shot. Okay guys, so I've kept you long enough for today. Today we've learned a lot more about thermochemistry, how to write a thermochemical equation, knowing again about exothermic and endothermic, but then we also talked about heats of fusion, heats of vaporization. We even showed a graph about how the temperature changes at a certain point, flattens out while it's going through a phase change, and then increases in temperature again. And we even solved a problem involving those phase changes. So I hope this was informative for you and I hope it helped you. If you need any more help, give me an email. Don't hesitate, and I'll be glad to help. I'm looking forward to seeing you guys really soon. Until then, God bless.